Hello, we're going to talk a bit more about sound. So we already looked at this figure, but as a reminder, the sound is a pressure wave that moves through any material, but this example is air particles with areas of compression and rarefaction. Rarefaction is just the opposite of compression, where there's a bit more space. Um, we hear sound because our eardrums are sensitive to changes in the pressure. So an object makes a sound, sending pressure waves through the air, and our ear picks it up. The wave itself travels through the medium, but each individual particle only moves a little bit, just like we saw with other waves, like waves in water and waves in a string, although I don't know that we technically looked at the individual particles. But this is because waves are really just pulses of energy traveling through a medium. And the only real requirement is that there is something for them to travel through. So, for example, your textbook talks or has like an example problem or something where it asks if the moon exploded, would we hear it? And the answer is no, because outside of the Earth's atmosphere, there is like space is a vacuum, meaning there is no air, there is no material for the sound to travel. So we wouldn't hear the sound the moon made because the sound can't travel through the vacuum of space. So we've talked about amplitude, which is how tall the wave is, or how far up or down it goes from the center. And that looks like this for traditional waveforms, taller. This is higher amplitude, more intensity, and louder if we're talking about sound. Whereas this is lower amplitude, less intensity, softer or quieter when talking about sound. When we're working with these simulations, we can also see how the amplitude changes with these. So instead of the side profile like this, we're looking kind of at the waves from above. And what we can tell is that the wave fronts, which is kind of like each wave as it goes, are much more distinct and brighter with this one over here, where they're like, I don't know how well you can even see this one. This one is very faint. There's just like barely these dark spots in here. So this is just showing another way of seeing the sound is much quieter here. It's only disrupting the air a little bit, where here it's much louder. So high intensity, low intensity. And then one other way we can look at it is with that, kind of initial diagram or video thing, clip, I guess. We saw how the particles or how the sound waves move through the particles. So we can also, in a situation like that, we can tell if something has a larger or smaller amplitude, like let's say if it's louder or quieter, based on the compression. So this up here, you can tell there are spots where it's more compressed and more stretched out. But it's obviously much less intense than below, where we have these, like there's no confusion about this having compression, spots of compression. Where this one, maybe if you weren't looking closely, you could almost miss it. And these have the same wavelength because if we're wavelength, remember, is peak to peak or whatever, any two of the same parts of the wave repeating. So the wavelengths are the same, but obviously this is a much smaller amplitude than this one because it's barely disrupting, barely sending a wave through these particles. Whereas here, it's very clearly sending a wave through the particles. So if this was sound, this one down here would be much louder than the one up top. So we've also been talking about wave interference. And we can look at this a little bit more too with sound. So disruptive interference, for example, which is when the waves end up in the same spot, but they're out of phase with each other. So it's the peaks and the troughs instead of peak and peak. So they end up canceling each other out. That is actually how a lot of noise canceling headphones work. They emit a sound that is out of phase with typical background sounds and cancel them out. So here are some kind of going from, we've looked at wave interference in the traditional waveform, but if we also look at it again in this kind of sound waveform that we've been looking at. So we have two waves in phase with each other. So the peaks are in the same spot, the troughs are in the same spot. Then when they meet, they amplify each other and increases the intensity. And then we have two waves that are out of phase with each other. So we have peak and trough, peak and or trough and peak. So when they meet, they cancel each other out, and we just end up with noise, like nothing. It just doesn't look like there was any wave there at all because they end up canceling each other out. There's this other concept of forced vibration. So if we strike an unmounted tuning fork, the sound from it may be rather faint, but if we hold that same tuning fork against a table after striking it, the sound is louder. And this is because the table is forced to vibrate. And with its larger surface area, it's able to set more air in motion, disrupting the air more and making us more able to hear that disruption. So again, the idea there is that we vibrate the tuning fork and then we press that vibrating tuning fork to a surface, and we're forcing the vibration into the surface. There's also this idea of natural frequency. So if we dropped a wrench on the floor and then a baseball bat on the floor, the sounds they make would be different because they each have their own natural frequency, or the frequency of vibration that they have when they are struck. And we know these are different materials, and it has to do with, the materials themselves. So the metal is going to have a different natural frequency than the baseball bat. So one more property here is resonance. So this is when the force vibration matches the natural frequency of the object. So the natural frequency is when you strike something, this is what it vibrates at, what frequency it vibrates at. So that's why metal sounds different than wood when it's struck. But you can create a resonance when you strike an object with a force vibration that matches its natural frequency. And what will happen is it'll dramatically increase the amplitude of the vibration. So this kind of relates to the process of pushing someone on a swing, which I know seems weird, but you just go with it. So you've likely seen this. If you push someone on a swing, you know that there is a sweet spot for where you should push them in their swing. If you push them when they've reached the farthest back point in their swing and they start to move forward again, you will provide a much better push than any other time in the swing. And that's because you're pushing them at the resonance of the swing itself. So it makes your push more effective. And I have another example of this, of resonance, actually like pretty significant example of resonance that occurred in Tacoma in the 1940s. Let's take a look. Okay, I've turned the sound off, but we're gonna watch this old-timey video. Shortly after the Tacoma Narrows Bridge was first completed in the 1940s, a wind came through the Narrows, which the Narrows is like that waterway, that like land space. And it started the bridge vibrating at its natural frequency. So it created a resonance, right? So when a resonance happens in a material, it continually amplifies the frequency. So, well, let's just see what happens. So here's people celebrating the unveiling of the Tacoma Narrows Bridge. People walking on it. But then, take a look here, that Wind going through the Narrows caused that vibration in the bridge that caused a resonance, which just meant that it would continue to increase in amplitude until eventually the bridge broke. And we'll see, like, look at those waves. And this was caused by only a 35-mile-per-hour wind. But it was just kind of bad luck of the construction that that wind was able to create so much damage due to the resonance. Um, and no one died, by the way. That car was stuck, though, fell into the water probably. And there's the bridge broken, pieces falling in. And they spent millions of dollars on this bridge. So they had to make another one where they didn't make those same mistakes. So that's all I have for you today, a short one. Yeah, have a great day.